Today's lecture is going to be on the third topic under thermochemistry, which is entropy. I understand that many of you have learned about entropy in the sense of AP physics, but today we're going to be learning about entropy and what it means for chemistry and chemical reactions. So first, let's give a good definition for entropy. Entropy is the measurement of randomness or disorder in a system. What we need to know is that the universe has a tendency to become more and more disordered. A classic example of this, albeit an analogy, is your bedroom. It might start off clean and ordered, but over time it tends to become messy and disordered. So let's suppose that we have four gaseous molecules in a glass tube with one bulb on one end and another bulb on the other end to better illustrate this idea of randomness or disorder. Here's the bulb with the four molecules. You'll note that there's 5 different ways that we can arrange the four molecules. We can have all 4 in the left bulb, 3 in the left, 1 in the right, 2 in the right, 2 in the left, 1 in the left, 3 in the right, or all 4 in the right bulb. Now, each of these arrangements can happen. If we were to have 4 gaseous molecules in these bulbs and monitor their presence in which bulb that they were in, they would be any of these 5 arrangements. There's no other arrangement we can have, assuming they can't be in the neck between 2 bulbs. However, disorder is not just the number of arrangements, but how frequently they can occur. If we were to name the 4 molecules A, B, C, and D, if they were all in the left-hand bulb, there would only be one way. The book calls these microstates, different ways that we can arrange these 4 molecules. Now, in the second arrangement with 3 bulbs in the left, 1 in the right, there are 4 different ways. You could have BDC, you could have ACD, ABD, or A, B, and C all in the left-hand bulb. We note that out of all of the arrangements, the third arrangement where there's 2 gaseous molecules in the left-hand side and 2 gaseous molecules in the right-hand side is the most possible arrangement of the molecules. There's 6 possible microstates out of the total 16 different microstates that there could be. If you get anything out of this video, understand this. Entropy means that whatever is most likely to occur will probably occur. So arrangement 3 is probably how we would see the 4 gaseous molecules at any given time. So from the previous example, we can see that the state that has the highest probability of occurring will occur. If we pull up that slide from a few seconds ago, it occurs because it has the highest amount of disorder. And disorder just simply means number of ways we can arrange things. Keep that in mind, the number of ways we can arrange things. So if we have the first orientation, there's only one way of existing. There's only one way that all 4 of those gaseous molecules can be in the left-hand side. While that third orientation, as we noted, has 6 different ways of existing. Another analogy that really shows entropy is rolling 7 with 2 dice. If you've ever played a board game that uses 2 dice like Monopoly or Risk or Settlers of Catan, you know that rolling 7 is the one that happens the most often. There's the most number of combinations for those 2 dice. So frequently, the game is oriented around the fact that the 7 is the most common dice roll because there's so many different ways. You can have a 1 and a 6, a 2 and a 5, a 3 and a 4, and all of those pairings but reversed. So let's talk about entropy in terms of chemical changes. It's fun to talk about them with dice and fictitious gaseous molecules. But like how the gas particles have a higher chance of occurring where there's greater disorder, chemical processes proceed towards greater disorder as well. So when a chemical process is going towards the state that has greater disorder or greater entropy, we call that process spontaneous. It's important to know that spontaneous doesn't mean that it will happen all of a sudden or instantaneously. Spontaneous just means that we know it will happen and we do not know when it will happen. For example, solids, liquids, and gases are 3 different states of entropy. Gases have the greatest amount of disorder. So if we have a liquid at 101 degrees Celsius, we know it's going to convert into a gas. However, if you've ever had to boil water to make pasta or some other dish, you know that you don't know when exactly it's going to boil, but you know that once it gets to that temperature, it will spontaneously begin to boil. Now, gases have a greater amount of disorder than liquids than do solids because the molecules require a certain amount of arrangements for solids and liquids, but do not require those arrangements for gases. We'll talk more about this later. We denote entropy, if you noted from the previous slide, by a capital S, like how enthalpy is denoted by a capital H, entropy is denoted by a capital S. When we have more disorder, we have a more positive value for entropy. That's a really important thing to know. When we have more disorder, we are going to have a more positive value for entropy. And much like other thermodynamic processes, entropy is often calculated by the change from initial to final state. While this video will not talk about how entropy is a state function, this is why it's the case, because we can use the initial and final states. We typically calculate delta S from the S of the products minus the S of the reactants, just like we did with delta H previously. So here's a question for you. Let's suppose we have the reaction I talked about earlier, the liquid turning into the gas. Would the entropy change be positive or negative for the following reaction? I'll let you pause the video. In 5 seconds, I'll tell you the answer. The correct answer would be that the delta S would be positive. That's because gases have greater entropy, greater disorder than liquids. And if you need to look back to that previous slide to show you why that's the case, the arrangement of the molecules for liquids are particular, while the arrangement for gas molecules are not particular. So that's why they have a greater entropy. Since the products are greater than the reactants, the delta S would be positive. This comes to the second law of thermodynamics. The first law of thermodynamics was this: the energy of the universe is constant. We can say that a bunch of different ways. We can say that energy cannot be created or destroyed, or we can say the energy of the universe is constant. However, entropy is different. Entropy is in any spontaneous process, the entropy of the universe must be increasing. That looks like this. The delta S of the universe is equal to the sum of the delta S of the system and the delta S of the surroundings, which must be greater than 0. So, if the delta S of the universe is positive, what that means is that the reaction as written is spontaneous. If the delta S is less than 0, if it's negative, it means the reverse reaction is spontaneous, which means that the forward reaction probably will not occur unless different conditions are met. Now, if delta S is equal to 0, it means that the reaction in the forward and the reverse are both spontaneous, which is also known as equilibrium. I understand that might sound confusing. We're only going to focus on the first two situations until we get to equilibrium in the second semester. But the first thing you really need to understand is that the delta S of a spontaneous process must be positive. Let's talk about the entropy of the system and the entropy of the surroundings. The spontaneity of a process depends on the temperature of the system. Let's go back to this classic example of H2O liquid turning into H2O gas. This is boiling. We know when it occurs. It occurs at 100 degrees Celsius. At 101 degrees Celsius, we would say that process is spontaneous. We call that boiling. However, at 99 degrees Celsius, the process is non-spontaneous. If you were confused from the previous slide on what non-spontaneous means when I said the reverse reaction is spontaneous, we know at 99 degrees Celsius, gaseous water vapor would condense into a liquid. So that means that the reverse reaction, right now we have a liquid going to a gas, but at 99 degrees Celsius, the process is what we would call non-spontaneous, or aka the reverse reaction is spontaneous. So the entropy of the system is dependent upon disorder and the temperature, but mostly upon the disorder. But the entropy of the surroundings is dependent upon the enthalpy of the chemical process, of the temperature of the system, and the surroundings. Whew, that's a lot of information. Let's break that down. The entropy of the surroundings is dependent upon the enthalpy of the chemical process and the temperature of the system and surroundings. So, while H2O liquid to gas at 101 degrees Celsius is a spontaneous reaction, the entropy of the surroundings is dependent upon whether that reaction is exothermic or endothermic. Let's break this down a little bit more, shall we? Let's suppose we have the following reaction. A plus B yields C, and let's say the enthalpy of this reaction is negative 100 kilojoules. This is an exothermic reaction, which means it's releasing 100 kilojoules for every mole of C that we're creating. In the first situation, let's say the temperature of both the system and the surroundings is 15 degrees Celsius. With 100 kilojoules of energy, that would greatly increase the temperature and therefore the disorder amongst the molecules of the surroundings. I've noted at a lower temperature, the energy flow will affect the surroundings to some degree. Let's say we have the same exact reaction with the same amount of kilojoules being created, but this time we're going to be at 1,000 degrees Celsius, something absolutely ridiculous. When at high temperature, the energy flow will not affect the system of the entropy of the surroundings as much. And this is because one, those molecules already have a great deal of energy, and two, they already have a great deal of disorder. So the temperature change will not affect the disorder of those molecules that much. Deriving from all of the information we've had previously, we get the following formula for the delta S of the surroundings, which is equal to the negative delta H divided by the temperature. Now, why is it negative? Because exothermic reactions have a negative delta H, which means if they're releasing energy and increasing the entropy, we would need to multiply that by -1 in order to get a positive value to express the increased entropy. Let's quickly recap what we've learned in this video. First, entropy is a measurement of disorder. We noted that gases have greater entropy than liquids, and liquids have greater entropy than solids. We learned from the second law of thermodynamics, the entropy of the universe is always increasing. And lastly, when a system has a positive net entropy change, the process is said to be spontaneous. Remember, that doesn't mean that we know it will happen right then and there at that moment. It means under those conditions, it will definitely happen. However, the time of that takes is not determined yet. We also noted that if it has a negative change, the process is said to be non-spontaneous. And what that means is that the reverse reaction will occur. Think back to that example at 99 degrees Celsius. The forward reaction of liquid boiling into gas will not occur at 99 degrees Celsius. However, at 99 degrees Celsius, the reverse reaction, that is gas turning into liquid, will occur. The last two things that we learned are these formulas. The first one is just the expression of the second law of thermodynamics. That is, the entropy of the universe is increasing, which is to say that the entropy change of the system and surroundings has to be greater than zero. And last, we learned how we can calculate the delta S of the surroundings, which is dependent upon the negative delta H of the reaction that's occurring within the system and the temperature of the system and the surroundings. In the next video, we'll take a look at the entropy of the systems a little bit more and examine how entropy being a state function help us calculate them. Thank you.